So last time we found the definition of a basis. A basis is going to be the set of linearly independent vectors that span whatever it is we're trying to find a basis for. So if we have a vector space and then we have a span of something, then we can have a set of linearly independent vectors will form a basis for that. We had our examples of subspaces of R2 and R3. And maybe we'll try to relate those ideas back to this stuff as we run into them. But in terms of subspaces, we found important subspaces that come directly from the matrix. So we have the row space, the column space, and the null space are all subspaces of R something, depending on the size of your matrix. But these are all obtained from a matrix. So they talk about a procedure to use to find a basis for each of those spaces. The very first thing we want to do is reduce it as much as we can, row echelon form. And we have to remember that if it's not a square matrix, or even if we knock off one or two rows down in the bottom, make them all zeros, then we'll have zeros in some of those rows. And so when we have something like that, we get some special subspaces and stuff. So we reduce, we find the reduced row echelon form, and here they decide to call it R. Use the non-zero rows of R containing the leading coefficient 1 or the leading pivot 1 to form the basis for the row space. And then use the column vectors of the original matrix A that correspond to the columns of R containing the leading 1 pivot columns to form the basis for the column of A, the column space. And then once you have, since you already have the reduced row echelon form, you can solve for the leading variables using the homogeneous system. And then if you have any free variables, you can set that equal to the parameters. So it turns out that those vectors that you multiply the parameters by turn out to be your null space, or turn up to form the basis for your null space. So this stuff probably doesn't make sense looking at all these words, so I think it might be better if we do an example and see how we can relate that to an actual problem. I don't know if we did one last time. Well, let me see if I can find a problem to do. Where are the problems? I don't know, number 17 or 18 or 19. Let's do number 18 first. So really the first step is to reduce as much as you can, and then it's a matter of analyzing the situation. And since this is a 3 by 3, it's also important to know the dimensions so that we can anticipate things. We're looking at R3 as your vector space for all the column space, the row space, and then the null space, since they're all coming from three vectors. This will give us allow us to take a look at, have a visual of what's going on, and relate it to our special two vector spaces, R2 and R3, where we can still visualize it. All right, let's do some row reducing. Let's see. Let's multiply the first one by -1 and add it to row 2. So the first row doesn't change. The second row makes that one go to 0. So -1 plus 5 is +4. Negative, that +1 plus 1 is 2. And then here we have, we'll do the same thing. We'll row 1 multiplied by -1, add it to row 3. That will give us a 0 for the first slot. -1 minus 1 is -2. -1, -1, that's +1 minus 2 is -1. And I think we have one more easy step here. We'll multiply, I guess we take a couple more steps. Since we want to fully row reduce this, we don't need to, but we should row reduce it. Let me start by, I'm going to have fractions here, but let me start by taking row 2 and multiplying it by 1/4 so that it'll make that into a leading coefficient 1. So this is where we get this fraction 1/2. And then from here, I'm going to use my pivot 1 here to get rid of the one above and below it. So I'm going to take row 2, and I'm going to multiply that by -1, add it to row 1, so that I have a 0 up on that slot. And then I'll take row 2 again. This time I'll multiply that by 2 and add it to row 3 to get rid of the second slot. So my second row didn't change. And my third row should change to 0 and then 0. And then multiply this by 2, I will get 1. 1 minus 1 is, that's 0. So it knocks up the whole denominator, or not denominator, but the whole thing's gone. So unfortunately, I can't get rid of these other two over here, so I think I'm done row reducing here because I don't have a 1 pivot here to get rid of the other numbers above. So this is as reduced row echelon as I can get. So now let's take a look at the row space. To get the row space, what they say in the instructions is that the row space is going to be the span of however many non-zero rows you have. I have, I'll write it vertically, 1, 0, -3 halves, and 0, 1, +1/2. So that's my row space. And this (1, 0, -3/2) together with 0, 1, +1/2. If I put the fancy curly brackets around it and say this is a basis so this is my basis. Now these two vectors are linearly independent, and so I have two linearly independent basis vectors, so I can say that this subspace is how many dimensions? This is a two-dimensional subspace in, where's my big vector space? R3. Okay, these are three vectors, so I must be living in R3, and this is two-dimensional space in R3. And so geometrically, what is this? 2 dimensions, so it's a plane. So if I draw these two vectors should be on the plane that it spans. Yeah. The free variable business will come when we solve for the null space, when we find the null space. Yes, we will have a free variable, but we don't access the free variable when we're looking for the row space. All right, row space good? Yeah. Well, we're two-dimensional subspace because there's two vectors here. And so the two vectors live in three-dimensional space. So that's what the three elements tell you. That it tells you that our big vector space is in R3. But since I only have two vectors that span it, it's only going to be a two-dimensional subspace, which is a plane. A plane passing through the origin, by the way, right? Okay, is this okay? Now, it turns out that, that step-by-step process tells us that we're supposed to select our non-zero vectors, row vectors here. But as long as we don't do any row swapping, we really could have chosen the non-zero vectors or the corresponding row vectors in the original matrix. But let's skip with what they say, and I think that's better. Column space. For the column space, what you need to do is you need to identify the leading ones in each row. And wherever those leading ones in each row are, you're going to identify them as the first and second column in this case. So I have leading ones in the first and second columns. Okay? But what I need to do is I need to go back to the original matrix A and pick out the first and second columns and then that will form my column space. So my column space will be from the original matrix 1, 1, 1, 1, 5, 1. They look like they're linearly independent. And if I try to see that, if I take a look at all three of these, then I'll see that it's actually linearly dependent, which means I could probably write this last column as a linear combination of the first two columns. Okay, we won't do that. We'll just say the span is equal to this, and they actually will form the basis. Now, it just happens so that they're living in R3 as well, but the original vector space for these things don't need to be the same if your matrix is not a square matrix. Okay? Yeah. Because when you row reduce it, the columns change. But the best you could say is that the original columns with the leading coefficients 1 would be, since you're not swapping the columns or anything like that, you're able to preserve the columns from the original matrix. But here, it's not going to be the same space as it is from the original. The row will be. And they suggest you take the row from the reduced matrix, but you take the column from the original matrix. So let's go back to our instructions here. To find the row, the basis for the row space, you find the non-zero row vectors of the reduced matrix. For the column, you find the columns that correspond to the leading coefficient 1s or leading 1s for each of the columns, the pivot columns, and then you get it from the original matrix A. Okay? All right. Now the last one is the null space. And what you need to do for the null space, before I put the equal sign here, I think I need to do a little bit of work. This is where we look for the free variables. So let's take a look at our matrix. 1, 0, negative 3 halves, 0, 1, positive 1 half, and 0, 0, 0. And what we want to do is we want to kind of back solve. Pretend that we are, let's squeeze in some zeros here. Pretend that we are looking at the augmented matrix, the homogeneous system, where you have zeros on the right-hand side, and then we're solving for this. So since we don't have a value for our z, that's what we're calling our variable z, our last variable, we have to assign it to be a free variable. So it looks like from the beginning we need our z equal to a free variable, and then you can solve for the rest of them. So I have y plus 1 half z is equal to 0. So y is going to equal to negative 1 half z, which we'll replace with t. And then for the first one, we have x minus 3 halves z is equal to 0. And again, we'll solve for x and then replace z with t. And so we have values for x, y, and z. Now remember, back when we were solving for these things, we would write it as x, y, z is equal to something plus t times, and then we factored out a t from all those things that have coefficients. So the z is equal to 1, the y is equal to negative 1/2, and then the x is equal to 3/2. So one thing to note, when you're doing this, this is this is exactly what the null space is. The null space are the x, y, and z values that would make this thing equal to 0, and we just found that. So this null space is actually, let me see if I can write it this way. This is the null space. By definition, the null space are the x, y, and z values that would make this equal to 0. Okay, so that's null space. And then, more importantly, it turns out that this vector over here, the null space is spanned by this one vector. So because it's spanned by this vector, you know how I've been writing the span of something, and that means those vectors are the basis. Well, this is actually the basis. And in this particular example, I only have a one-dimensional null space. So we can say null of A equals span of this one vector, 3/2, negative 1/2, 1. So that means this vector, 3/2, negative 1/2, and 1 is a basis. Forms a basis for the null space. Now, if that forms a basis and that is a span, yeah? Yes. Well, no, I don't. When I say basis, I mean non-zero vectors that span the subspace. So you can't have 0 as part of your basis. But the space itself, the subspace itself, always passes through the origin. Okay? All right. Since since the null space is a span of this, really you can make this look a little nicer and get rid of the fractions maybe by multiplying by 2. So if you say the span of 2 times that basis, whatever that is, since t is an arbitrary free variable, I can have that to be anything I want. But if I just multiply this basis by 2, that'll give me the exact same space. Because I have a one-dimensional space, I just have one vector. Whether that vector starts off with a certain length or shorter or longer, it's still, the span of that is still the scalar multiple of that, so it's still going to span the same space. So this is the null space. Okay? So there's a lot of interesting scenarios here. In this case, we got a set of zeros down in the bottom after we row reduced it. If we didn't get zeros in the bottom, we start off with a square matrix, we didn't get zeros in the bottom, what can you say about your null space? Here, what if we, let me write it down. Suppose you have a 3 by 3 matrix. This is your A. And then you row reduce it, they call it R. And then you row reduced it where you don't have zeros in any of the rows, right? How would the row reduction look like? Reduced row echelon. Yeah. So if this has no zero problems, then this would just be the reduced form. Okay? So if this in fact happened, what do you think is going to be your row space? What's the basis for your row space? Well, row space will be exactly R3. But if I ask for a basis, I need some vectors. No. 1, 0, 0. 0, 1, 0. 0, 0, 1. So the span of this, or the base, I guess this, I'll just say the basis. So the row space can have this for your basis. Which means, how many dimensions is this? It's a 3-dimensional subspace in R3, which means it must be all of R3. Okay? What's a column space? Well, you have to look at which columns have the pivot column 1 and which ones have that. All of them. So I would take if I call this V1, V2, and V3, I would just take all those V1, V2, and V3. Anybody give some more insight to this? It's what? It'll span all of R3 again. So this is a 3-dimensional vector space again. Okay? Does that make sense? If it spans of all of R3, that probably means I could just, instead of using this random basis, I probably could use the same thing. Because as long as if I'm in R3, I could take any 3 linearly independent vectors, and then that would span all of R3. All right, more interestingly, I don't know if it's more interestingly, but the null space. It's the x, y, z that would make this vector, or make this matrix go to 0. So, do I have any free variables? I don't have any free variables. So I go out and solve for this. I say, oh, z must equal to 0. x must equal to 0, y must equal to 0. Right? Let me say that again. X must equal to 0, y must equal to 0, z must equal to 0, no free variables. And all this is obtained from your reduced matrix. So, does this make sense? Can I have this? How many dimensions is this? 0. This is a 0-dimensional vector space. It looks like a vector 0, right? What? What? Huh? What? It does exist, and it's 0, exactly 0. The origin. You have one point that would make this matrix go to 0. And that's what it's saying. I'm going to look back at our old notes. A 0-dimensional space is when you have one point. Oh, I did it over here. So this is our summary of the subspaces in R2 and R3. If the only thing you have in that subspace is a 0 vector, then that's a 0-dimensional subspace. And if it's if you have one non-zero vector in there, then it's a 1-dimensional subspace. Whether you're talking, so it's a line. Whether you're talking of living in R2 or R3, we have lines in R2 and R3, so that's a 1-dimensional subspace. If it's spanned by 2 vectors, if you're on the plane, then it's everything in the plane. If you're in 3D, then it means it's a 2-dimensional plane in 3 dimensions. And then finally, if you're in R3, and then you have 3 linearly independent vectors, then it's all of R3. So it is possible for us to have a 0-dimensional subspace that only has that 0 vector as our point. So that's what's happening here. Our null space is a 0-dimensional subspace because it's the only point. It's the only vector is a 0 vector. That's the only vector that would give you a 0 for your output. Okay? That's your null space. Any questions? All right. So more interesting problems would have like non-square matrices, like I was saying. I think you guys can look for some more of those examples in the textbook or in your homework assignment. So let's see if we can move on here. Can you move on after that? A rough example. That was a good example. All right. There's a bunch more theorems and definitions that tie in everything else, and then we're going to have one big theorem that tries to tie everything else that we've been learning. So let's take a look at starting with the basis theorem. Let S be a subspace of Rn, then any 2 bases S have the same number of vectors. Okay. Remember, a basis is a set of linearly independent vectors that span your subspace. So they have to have the same number of vectors. I won't talk much about that. You can try to prove it if you want. What you can do is you can assume that there's, this would be a good proof by contradiction. You can assume that there's two bases and then one of them has more than the other, and then you'll get a contradiction somewhere. So if you're doing an honors project, for example, and you're doing proofs, this would be something to do. Dimension, we've been talking about dimension all along, so I think that gives me the opportunity to just tell you what it is instead of talking much about it. So the dimension is the number of linearly independent vectors that you've collected to span your space. So in nicer terms, it's the number of basis vectors you have that span your space. So that's dimension. We have another theorem. This one's an interesting one. And we saw it in the two examples. So I didn't point it out, but we did see it. It turns out that if you have any matrix, regardless of what size, our matrix, the matrix that we were dealing with happened to be square matrices, but they don't have to be square matrices. But it turns out that your column space and your row space have the same dimension. So imagine if you have a 3 by 5 matrix and then you reduce it and you find your space for your column and your vectors, or your column and your row space. You found your basis vectors. You'll have the same number of basis vectors every single time for your row space and your column space. And it has to do when you do the reduced row echelon form, you have the leading pivot columns. Just you're essentially counting your pivot columns. All right? So that's another interesting fact. Another definition. Since the row space and the column space are the same, they give it a special name, the dimension that is. The dimension of the row space and the dimension of the column space are the same number, so they just decided to call that rank. So the rank of the matrix is the dimension of the row space or the dimension of the column space. And the easiest way to do this, have we defined rank before? I thought we did. Oh. Like, ooh, that's rank. So the rank is, after you row reduce your matrix, is really the number of non-zero rows that you have left. So that's the rank. I thought we had defined that earlier. But if we haven't, that's the same thing as looking up the number of non-zero rows you have. That's how you get your row space. So it's the number of non-zero rows in your reduced row echelon form. And since the row space and the column space are the same, if you take the transpose of it and then you do the row reducing, you should get the same number. So the transpose, you switch the rows and columns, so whether you switch the rows and columns or not switch the rows and columns, whatever you reduce, you're going to get the same number of non-zero rows. All right. A whole bunch of definitions and theorems. Where's the big one? Oh. So here's a couple more, a definition and a definition and a theorem about the null space. just like rank is the dimension of the row space, nullity is the dimension of the null space. Okay? So the null space, then, the null space is a whole space, just like the row is a space, the row space is a space, and the column space is a space. And then we give row space and column space a special name, the dimension of that a special name called rank. People decided that they had to give the null space a special name also. The dimension of the null space is the nullity. So if we want to distinguish the space themselves, you guys understand my subspace notation? S/space. So given your matrix A, the subspace that we can refer to as the row space is called row parentheses A. That's your official name for that, for the row space. And the corresponding dimension is the rank. The column space is denoted by col A, and the dimension happens to be the same as the row space. And then the null space is denoted by null parentheses A, and then the dimension is nullity. Now, all that means is that these are numbers, and these are actual spaces, vector spaces, if you want to think about it this way. Subspace of a vector space is in itself a vector space, so by definition, it is a vector space. Let's call it V space for vector space. But the point is that they want to distinguish when you're describing a space versus when you're looking at a number that describes the dimension of a space. So that leads us to the rank theorem. So M is the number of rows of a matrix and N is the number of columns of a matrix. So it turns out that the rank of A plus the nullity of A is going to equal to the number of columns that you have in your matrix. So this is turns out to be a fairly important theorem in theory, and also when you're doing this and you're finding the basis for the rank and nullity or the null space, and then you're getting all these numbers. This is a easy, quick way to check if you're getting it correct. In our example, when we got the bottom row of our matrix to be all zeros, we found that the rank was equal to 2, or we found that the column space was 2 and the row space had dimension 2, and then we found that the null space had dimension 1. Right? In fact, if we look at these examples, we have a 2-dimensional row space, 2-dimensional column space, because the row space and column space are the same. So you can say in this example that the rank equals 2, right? And then it turns out that this has 3 columns. The original matrix was a 3 by 3 matrix, so it had 3 columns. And it turns out that the nullity is equal to 1. So that satisfies our rank theorem. Similarly, our row space and our column space for this is 3-dimensional, so rank is equal to 3. And it turns out that we have a 0-dimensional null space. And so that still satisfies our rank theorem. Okay? So, quick way to check if you're doing things correctly, you just make sure that whatever it is you're dealing with matches your columns, the number of columns. The rank and the nullity should add up to the number of columns. Questions? All right. So now we have our big theorem for the course that kind of is continuing to grow. I think there was a version of this theorem last chapter that had like 5 or 6 things in them. And so we're going to add on, now that we have more language about matrices and systems of linear equations and stuff like that. So we're just going to add on to it. And then later on, once we learn more stuff, we're going to continue to add on to this. So I don't know if this is the formal name for it, but this is what the book calls it, the fundamental theorem of invertible matrices. And what that means is that if you have an invertible matrix, then there's a whole slew of things that follow. That means AX is equal to B has a unique solution. That means AX is equal to 0, our homogeneous system, has only the trivial solution, which means the null space is 0, or the null space is, the nullity is 0. I guess that's G over here. We'll get there. The reduced row echelon form, by the way, this is for square matrices. So the reduced row echelon form will have to be the identity matrix. Because if this is invertible, you're not going to have any 0 rows after you reduce it. So that means this will have to be the identity matrix. And you could also write A as a product of elementary matrices, which means there's an LU decomposition for this. It doesn't say that here, but there's an LU decomposition for a lot of things. But in this case, it would follow for this one also. The rank is exactly the number of columns because the nullity is 0. The column vectors themselves are linearly independent. So if we take a look at just identifying the column vectors, they're linearly independent because they form a basis for the column space. So if they form a basis, by definition, they should be linearly independent. The column vectors span Rn. The row vector is also linearly independent, and they also span Rn because this is an n by n square matrix. So I think that's it for now for the fundamental theorem of invertible matrices. We're going to talk about eigenvalues and eigenvectors in the next chapter, and when we do, we'll include language about eigenvalues and eigenvectors and add on to this list of all equivalent things.
You only go up to chapter 5, right? 6.
Whatever. Okay, so it's kind of weird that this list is something that really should have been, brought out in front, but they can't prove any of this in the beginning because we don't know what column space was. We don't know what rank and nullity were back then, and so it's only up to now that we were able to bring this up. But it really ties into everything that we've discussed from chapter 1 and 2. When we're talking about systems of linear equations, and then so when we talk about system of linear equations, you can write your augmented matrix as A with a B in it, and then you can similarly you have this homogeneous system where the right hand side would be all zeros. Okay. So the idea in a big theorem like this is to, in terms of trying to prove it, you prove equivalences, and a lot of this was proven because I think they went through 1 through A through D is the first glimpse that we saw this as. We've definitely seen B and C together, but I think since we just barely started talking about inverses and matrices, then maybe that's where A started to come in. But now that we talked about subspaces, all this other stuff makes sense to us. All right. Is there more? There's more. Thought we were done. So let's throw out a couple more theorems for your notes. I don't know if it's really worth talking about any of this. It might be important for later on. Let's see. If you have an M by N matrix, then the rank of the transpose times A is equal to the rank of A. And then it turns out that this product is an N by N matrix, right? If A is an M by N and AT is an N by M, so AT is an N by M matrix, multiply that times A, which is an M by N matrix, then the product AT times A is equal to, remember these two cancel, and then you have N by N. So it turns out that it has the same rank as the original matrix A. So if it has the same rank as the original matrix A, and then your nullity is 0 for that, then you can say A is invertible, and it turns out that AT times A is also invertible. Okay. Yeah, I don't know if that's very interesting. The next theorem, S is a subspace of Rn and B is a basis for S. Then every vector V in S, there is exactly one way to write V as a linear combination of the basis vectors. Now this one comes into play kind of subtly. Later on when we talk about expressing things with respect to the basis. Because you might have two vectors that span something, that span a two-dimensional space, and then you could have another set of two vectors that spans another space. So in this case, we say that there's a unique way of writing it. I think this is an important theorem that we'll come back to when we start studying change of bases and making your basis nice and neat for us. So we'll come back to that later. Yeah. Using AX.
So AX equals B is B in a parameter? Or
No, B is an actual vector that you're getting. I think it's kind of like the same thing as this. Yeah. Yeah. Yeah.
So if you have a parameter of 0, does that mean and your rank is equal to n, and you have
Then
linearly,
yeah, and then so 0, 0, 0 is the only way to get there. Yeah. What's this? Oh. Let S be subspace of Rn, and B is a basis, and V is a vector in S. Then we write V is equal to that. We know that there's a unique way of doing this. Then C1, these coefficients are called the coordinate vectors or coordinates of V with respect to the basis. All right, now I feel like we really do have to come up with an example. So these two, this combination of theorem and this definition that comes out of the theorem is something that we've been doing all along, actually, whether you knew it or not. But it turns out that they're able to put it in a nice theorem definition form. Let me show you an example of this. And I'll show you an example by talking about two basis vectors for R2. So let's do our example in R2 because it's easy to visualize and you guys know everything about R2. In R2, we said that if we have two linearly independent vectors, we can span the whole space. And we know that the whole space is also a subspace of the whole space. So let's talk about two vectors that span the exact same thing. So give me two random vectors in 2D. I guess we should do a script B. B1. What? 2, 3. 6, 5, as long as they're linearly independent. Right? So this is one basis. So as long as they're linearly independent, they span all of R2. And let's take a look at another basis. How about the standard basis? You know what I mean by the standard basis? Okay. The standard basis would be 1 unit in the x and 1 unit in the y. So 1, 0, and 0, 1. Now let's pick some random vector in R2. What? Just give me a point in R2. 9, 3. Okay. So it turns out that with the standard vector, when you say 9, 3 as a vector, this is your, what do they call it? This is your coordinate vector with respect to the standard vector. Coordinate vector with respect to, WRT, with respect to the standard basis. Okay? Now, if you want the coordinate vector for this 9, 3 vector with respect to a different basis, you have to do some solving. And so what you would do, let's do this in a different color. What you would do is you'd basically see if you can write this as a linear combination. 2, 3, 6, 5, 9, 3. You guys know where I got this from? So we'll call this V1 and V2. You say C1 V1 plus C2 V2 is equal to our vector V. And then you write a system, and then you write it as augmented matrix. This is what you get. And then you row reduce this. I'm not going to row reduce that. So if I row reduce that, I get this, which means x is equal to, or C1 is equal to negative 27 over 8. And C2 is 21 over 8. Okay? So that means I can write my vector V as negative 27 over 8 and 21 over 8 with respect to that basis. So if I have this basis tucked away somewhere, and then I write my vector instead of a vector with just 9, 3 or 9, 3 with a sub basis for my standard basis, if I write it as this B1, then I know that it's equal to the linear combination of this with this thing as its coefficients. It's not quite the same as modulus, but it kind of is modulus. It's using, it's not the same as modulus, never mind. Okay? So that's what this will be a lot more valuable if we have more control over our basis and changing our basis. And so the change of basis business happens around Chapter 5. And so this will become a lot more important to us later on. All right. I think that's it for today. Let me tell you what's happening. So we were able to tackle the fundamental theorem of invertible matrices. When I say tackle, I just put it up there and showed it to you. But there you saw it. And then tomorrow or on Wednesday, we're going to talk about linear transformations. And then you will have your exam a week from Wednesday. And I'll tell you, I'll have a review sheet and I'll have an outline for the exam so you know exactly what to expect. Okay. And I'm hoping that I wrote the exam so that's a little bit shorter than last time. I hope that's going to be the case. We'll see. A week from Wednesday, yes. All right. A week from Wednesday. It's next week on Wednesday. All right. See you guys on Wednesday.